Hi guys, we are from School of Agriculture in SR University, Asanpatli. We are from agriculture first year. We do soil science experiment.
Title of the experiment is to describe about soil moisture content using tensiometer.
Aim to determine the soil moisture using with tensiometer. Material requirements: screw agar, tensiometer, distilled water.
Here, first we have to dig a hole with the help of screw agar. Place a tensiometer in the digging of hole.
Now we have to open the cap of tensiometer and fill the distilled water up to certain point. Now we have to close the Now we have to open the pit and lift the tensiometer.
Hi everyone, we are from School of Agriculture from SR University first year. Now we are going to do soil science experiment. Title of the experiment is determination of soil moisture content by using gravimetric method. Aim of the experiment to estimate the moisture content present in the soil by gravimetric method. Instruments required for this experiment: aluminium box, soil sample agar, weighing balance. Hot agar oven. Now we are going to take aluminium empty box. Now we are taking the soil by using the agar. Now we are taking the soil into the lid. Now we are going to take aluminum box plus soil weighing balance. Now we are going to put the aluminium box with soil in a hot air oven for 105 degrees 24 to 48 hours. After the 24 hours, we are going to take the aluminium box in hot air oven. We are going to take the oven dry weight. Generating the moisture content in dry wet basic is the ratio of mass of water to the mass of dry soil. As we already calculated the mass of dry soil, now we have to find the mass of water. The mass of water is the difference between the wet mass of soil and dry mass of soil. Next, the moisture content is wet basic is computerly similar. The only difference is the difference in the mass of soil is divided by the mass of wet soil. The moisture content and volume basic is calculated by the volume of water divided by volume of soil. As we know, the density of water is equal to the 1 gram of cubic centimeters. We can substitute as the mass of water divided by volume of soil. This is the way to record the data to calculate the moisture content and different soil dense. M1 is the mass of empty moisture can. M2, the mass of can with wet soil. M3 is the mass of can with dry soil. And the difference between M2 and M3 is the mass of water. The N, moisture content can be calculated by dividing the difference between M2 and M3 divided by the difference between M3 and M1 multiplied by 100. For each sample, finally, the moisture content of each depth is calculated by obtaining the mean values of reflectors.
Earth interior. The Earth interior is not a single structure. The Earth interior have different concentric layers. Normally crust, mantle, core. The Earth interior is classified into two types. One is mechanical division and another is chemical division. In mechanical division we can see lithosphere, asthenosphere, mesosphere, mantle, outer core and inner core was divided. In chemical classification in the Earth interior is crust, upper mantle, lower mantle, outer core and inner core are classified. Mechanical classification of Earth layers. Lithosphere is the Earth interior outer layer. Its thickness is 100 to 120 kms and crust, mantle also included. Lithosphere all have the tectonic plates. In these plates, tectonic movement will form. In Earth, tectonic movement occurs due to primordial heat. In Earth interior, radioactive elements located. Lithosphere after there is another mechanical layer. Asthenosphere generally present in mantle upper and it is highly viscous, mechanically weak and ductile. Below the asthenosphere, mesosphere mantle is located. In this, Earth volume is 87%, mass 67% will hold. In this layer may have coffee temperature because in this convective current generate will happen, tectonic plates will move and media will generate. And the outer core or inner core, they too have similarly core. We can study two layers significances. Outer core is have 4 layers and outer core cover 4 layers than the inner core. Nife means nickel or iron, it was made up. Shortcut we call it as knife. Outer core is present in the liquid state, inner core is slightly below the outer core. It is also made up of nickel and iron. But here nickel use it very less. Here the temperature is 6000 degrees Celsius. Here the pressure is high. So it is present in solid state. Chemical classification of Earth interior. Crust is the outermost part of the Earth. Its width is 8 to 40 kms. Here the interesting part is its width in continents and in oceans are different. In oceans, crust width is 8 kilometers, relatively less than continents 40 kilometers. Seal, silicon and aluminium made up of. Mantle, in between crust and mantle discontinuity, it is present. We call it as Moho discontinuity. Thickness of mantle is 2900 kilometers. It is made up of sima, silicon and magnesium. Mantle is divided into two parts, upper mantle and lower mantle, and in between continuing is known as repeated discontinuity. Core is the innermost layer of the Earth. Gutenberg discontinuity. It is the layer which separates the mantle core, is occasionally known as barysphere. This is the most densiest layer of the Earth. Its density is 9.5 to 14.5 gram per centimeter cube. Outer core and inner core discontinuity is known as Lyman discontinuity. We know only limited about Earth's interior because high temperature of the Earth.
Pressure plate apparatus working principle. This is pressure plate apparatus instrument. These are the apparatus required for working principle of pressure plate apparatus. First one, metal chamber with ceramic plate. Second, a compressor. Third, pressure regulators. Are few images of pressure plate apparatus. Some uses of pressure plate apparatus are the air pressure to remove water from soil samples, allowing for the measurement of soil moisture and water retention. As it works, firstly place saturated soil samples on ceramic plate in the metal chamber, then apply air pressure through a compressor gradually, remove water from the soil samples. Control the air pressure to achieve equilibrium between pressure and soil water tension. Lastly, remove the soil samples and oven dry them to determine moisture content. Few points of pressure plate apparatus. A pressure plate apparatus is a piece of equipment that can be used to measure soil moisture retention and to analyze forces on the feed. Pressure plate apparatus is used to establish moisture retention for any soil type. It is reliable means of removing soil moisture under controlled conditions from the soil samples throughout the plant growth range without disturbing the soil structure. Pressure plate apparatus are to determine soil water retention, available water capacity, hydraulic capacity, field capacity, classify soils, survey soils, optimize irrigation and drainage, calibrate soil water measuring devices. Of pressure plate apparatus are field capacity determination, permanent wilting point determination, soil water retention curve. Of it are accurate measurements, controlled environment, flexibility. Provides precise values of metric potential, allows for controlled laboratory conditions, can be used for various soil types and samples. Sample size is only small soil samples can be used. Time consuming is the measurement process can be slow. Requires calibration. The pressure plate apparatus need to be calibrated before use. These are some limitations of pressure plate apparatus.
Now we are going to learn about Munsell color chart for soil science. What is Munsell color chart? It is the visual representation of the Munsell color system, which is standard way to specify color. Contents we are going to learn in this video is introduction of Munsell color chart, hue, value, chroma definitions, color and soil properties, case studies in soil color analysis, challenges in soil color assessment. What is Munsell color system? The Munsell color chart is a standardized color system used in describe soil colors based on three components: hue, value, and chroma. It was developed by Albert H. Munsell in early 20th century and is widely used in soil science, geology, and agriculture for soil classification. Importance in soil science. Soil classification helps in categorizing soils based on color, which is indicator for soil properties. Soil fertility and organic matter. Darker soils usually indicate higher organic matter content. Moisture content. Color changes with moisture. Wet soil appears darker than dry soils. Iron and oxidization state. Red and yellow hues indicate oxidization, while grayish color indicates poor drainage or waterlogging. Soil health and degradation. Changes in soil color can signal erosion, pollution, or degradation. Components of soil. Hue represents the dominant wavelength, such as R represents red, YR represents yellow red, and Y represents yellow in soil classification. Value represents the lightness or darkness of the color. Chroma represents the purity or intensity of the color. Soil is typically written as hue, value, chroma. Example 10YR 5/3 means a soil with 10YR hue, value of 5 and chroma of 3. Applications in agriculture. Soil quality assessment. Farmers can determine soil fertility and organic matter based on color. Irrigation planning helps identifying poorly drained or waterlogged soils. Nutrient content. Soil color provides clues about nutrient content. Erosion studies helps track changes in soil properties due to erosion. Soil suitability assists in selecting suitable crops based on soil conditions. The color aspect. In Munsell color system, hue refers to attribute of color that allows us to distinguish between different types such as red, yellow, green, blue, or purple. It is essentially the name we assign to various colors based on their position in the color spectrum. Significance of hue. Color identification. Hue serves as the primary means of identifying and differentiating colors. For example, it enables us to distinguish a red apple from a green one. Emotional and psychological impact. Different hues can evoke specific emotions or associations. For instance, red is often linked to excitement or urgency, while blue may convey calmness or truthworthiness. Formation of hue. Hue is determined by a wavelength of light that an object reflects or emits. When light strikes an object, certain wavelengths are absorbed and others are reflected. The reflected wavelengths correspond to specific hues that we perceive. For example, an object appears red because it reflects wavelengths associated with red hues and absorbs others. Practical example. Consider a painter selecting colors for a landscape to depict a vibrant sunset. The painter might choose hues like reds, oranges, and purple. Each hue selection contributes to overall mood and realism of the scene, demonstrating a practical application of understanding and utilizing hues in art and design. Value. The lightness and the darkness. In Munsell color system, value refers to the lightness or darkness of the color, ranging from pure black to pure white. Impact of value on soil properties. Organic matter content. Soil with lower value numbers typically contain higher organic matter, which enhances soil fertility and structure. Soil horizons. The value can indicate different soil layers. For instance, a horizons are darker due to organic material, while E horizons are lighter, reflecting leaching process. Value in soil classification. Soil classification system utilize value measurements to identify and categorize soil. For example, in Brazilian system for soil classification, a soil is classified as grey agrisola when it represents a hue of 7.5 YR or higher, a value of 5 or higher, and chroma less than 4. Real world implications of value in Munsell color system. Agriculture. Understanding soil value helps farmers access soil health and make informed decisions about crop selection and management practices. Environmental assessment. Soil value measures assist in evaluating land degradation and planning for soil conservation efforts. Construction. Builders and engineers use soil value information to determine soil stability and suitability for various construction projects. By providing a standardized method to access soil color, the Munsell color system's value component plays a crucial role in soil science, influencing classification, management, and utilization practices across multiple industries. Chroma, the intensity of color. In Munsell color system, chroma denotes the intensity or purity of a color, reflecting its saturation level. In soil science, chroma is a vital parameter for evaluating soil health and properties. Understanding chroma in soil health, iron and manganese content. Soils with higher chroma values often indicate the presence of oxidized iron and manganese compounds, resulting in more vivid colors. Conversely, low chroma values may suggest reduced conditions or poor drainage and aeration. Low chroma values, especially grayish hues, can signify poor drainage and waterlogged condition, leading to reduced soil aeration and potential root health issues. Chroma in soil analysis. Standardized assessment. The Munsell color chart provides a consistent method for determining soil chroma, facilitating uniform soil evaluations across different regions and studies. Soil classification. Chroma measurements assist in classifying soil horizons and types, aiding in soil mapping and management practices. Case studies involving soil chroma. Smartphone based soil color determination. Research has explored using smartphones to capture soil images and determine Munsell color attributes, including chroma digitally. This approach aims to reduce subjectivity and enhance accuracy in soil color assessment. Lighting conditions and soil color accuracy. Studies have evaluated how naturally lighting variations affect the accuracy of visually determining soil color using Munsell color charts, highlighting the importance of consistent lighting for reliable chroma assessment. By accurately assessing chroma, soil scientists and land managers can gain insights into soil conditions, informing decisions related to agriculture, construction, and environmental conservation. How to read Munsell color chart. To properly use Munsell color chart in soil classification, collect a soil sample. Take a fresh soil sample from the desired depth. Moisture or dry soil sample to a standard condition for accurate comparison. Choose a good lighting condition. Natural daylight is best. Artificial lighting should be standardized for consistency. Compare with the Munsell chart. Hold the soil sample next to the color chart and match the color. Identify the hue, value and chroma. Record the notation. Example 10YR 4/2. Consider moisture effects. Dry and wet soil samples can different colors. Record both dry and moist readings for better accuracy. Field applications of Munsell color chart. Soil surveys and mapping used by soil scientists and agronomists to classify and map soil types. Agriculture and farming helps farmers to assess soil quality and fertility. Environmental studies identifies contamination, erosion or wetland boundaries. Construction and engineering determines soil suitability for building foundations. Common mistakes to avoid while using Munsell color chart. Incorrect lighting. Using artificial or shaded lighting leads to wrong color interpretation. Ignoring moisture effects. Soil appears darker when wet, so always compare dry and moist samples. Using dirty or stained charts. A faded or stained chart can cause miscalification. Not standardizing view angle. Holding the sample at different angles can distort perception. Properties of Munsell color chart. Physical properties. Texture and structure. Darker soils often indicate fine textured soils with high organic matter, while lighter colors suggest sandy or silty soils. Moisture content. Wet soils appear darker while dry soils are lighter. Drainage and aeration. Red and yellow soils indicate good drainage, while grey and blue soils suggest poor drainage or waterlogging. Chemical properties. Organic matter. Dark brown to black soils contain more organic material, improving fertility. Iron and oxidization state. Reddish soils indicate iron oxidization, while grey-blue soils suggest reduced iron. Salinity and pH. White or light colored soils may indicate high salt or carbonate accumulation affecting soil pH. Biological properties. Microbial activity. Darker soils support more microbial life due to higher organic content. Decomposition rate. Rich organic soils show active decomposition benefiting plant growth. Root penetration and growth. Well aerated soils promote deeper root growth, while grey or malted soils indicate root stress. Research findings on Munsell color chart in agriculture. Soil fertility crop yield. Studies shows that darker soils support better plant growth, while pale or grey soils indicate low fertility. Soil erosion tracking. Research confirms that changes in soil color can help monitor erosion and degradation over time. Precision agriculture. Digital soil color analysis improves site-specific farming practices, optimizing fertilizer and irrigation management. Impact on agriculture. Better soil classification helps farmers choose the right crops based on soil types. Nutrient management indicates organic matter content and nutrient availability. Water management guides drainage and irrigation strategies. Erosion prevention identifications at-risk areas for conservation practices. Environmental implications. Wetland conservation identifies poorly drained soils to protect wetlands. Dark soils with high organic content help in carbon storage, reducing greenhouse gases. Pollution detection. Unusual soil color variations can indicate contamination from industrial or agriculture waste. Future directions. AI and machine learning. Automatic soil color classification for precision farming. Remote sensing and GIS integration. Using satellite data to map soil color and properties on a large scale. Digital soil mapping, creating real-time interactive soil health databases. Climate change adaptation, monitoring soil changes due to climate shifts and guiding sustainable land management. Challenges and solutions in using the Munsell color chart. Subjectivity in color perception. People see colors differently due to eye variation, lighting, and bias. Solution: use digital color sensors, standardized lighting, and training to improve accuracy. Environmental factors: moisture changes soil color, minerals, organic matter, and pollution affect color. Solution: compare dry and moist samples, use spectroscopy for precise analysis. Standardization issues: soil colors vary by region, and Munsell charts have limited swatches. Physical charts fade over time, reducing accuracy. Solution: use digital soil databases, remote sensing, and updated charts for consistency. Overcoming challenges: subjectivity, digital sensors, training, standardized lighting. Environmental effects: compare moist, dry samples using spectroscopy. Standardization: expand soil databases, integrate remote sensing. New digital tools and AI are improving soil color classification for agriculture, climate studies, and land management. Future of the Munsell color chart, innovations and applications. Technological advances. Digital soil color sensors devices like colorimeters and spectrophotometers eliminate human error. Mobile apps, AI apps analyzes soil color using phone cameras, improving accessibility. Satellite and drone imaging, remote sensing helps map soil colors over large areas for precising farming. Integration with other data. Combine soil colors data with climate, moisture, and land use patterns. Big data and AI use machine learning to predict soil health and fertility trends. Soil climate models link soil color to environmental changes and carbon storage. Educational initiatives, digital training modules, online courses teaches soil scientists and farmers how to interpret soil color data. Citizen science project. Farmers and students collect and share soil color data for research. Smart agriculture integrates Munsal data to precision farming for better crop decisions. Vision for the future. Fully digital soil classification. AI driven soil analysis replacing. Conclusion. The Munsal color system remains an essential tool in soil science, helping classify and interpret soil properties based on hue, value, and chroma. By analyzing soil color, scientists can assess drainage, fertility, and mineral composition. However, challenges such as subjectivity and environmental variability highlight the need for technological improvements in soil color assessment. Thank you.
Hello everyone, here is my soil science presentation on field method. Here our aim is to determine of a soil texture by field method. Materials required: electronic weighing balance, distilled water, measuring scale, sieve. Step 1 in the procedure: ensure the soil sample should be sieved in 2 mm sieve. Measure the soil sample up to 25 grams in the electronic weighing balance. Step 2 in procedure: take 25 grams of soil in the hand, add water slowly, and knead soil to wet all aggregates. Soil at proper consistency moldable into a mud ball.
Here 5 soil samples are collected from 5 different locations.
and each soil sample is molded into a mud ball.
If there is a ball formation, we can conclude that the soil is not sandy. Step 3 in the procedure. Place ball of soil between thumb and forefinger. Gently push the soil with the thumb and squeeze with upward into a ribbon. From a ribbon of uniform thickness, we allow the ribbon to emerge and expand over the forefinger, breaking from its own weight. If there is a ribbon formation, we can conclude that the soil is not loamy sand and silt. Step 4 in the procedure. Measure the length of the ribbon with measuring scale. The length of the ribbon in the sample 1 is 2.3 centimeters. And in the sample 2, 3.5 centimeters, in the sample 3, 4.5 centimeters, in the sample 4, 5.5 centimeters, in the fifth sample, 4.8 centimeters. Step 5 in the procedure. Excessively wet a pinch of soil on the palm and rub with forefinger.
Conclusion of soil samples. Here is the result given below in the table as: Sample 1 belongs to silt loam as it is predominant with gritty texture.
Sample 2 belongs to clay loam as it is not predominant with both gritty and smooth texture. Sample 3 belongs to sandy clay loam as it is predominant with gritty texture. Sample 4 belongs to silt clay as it is not predominant in gritty nature but predominant in smooth texture. Sample 5 belongs to silty clay loam as it is not predominant in gritty nature but predominant in smooth texture. Soil science presentation given by V. Ashwita, E. Rajeshwari, A. Sri Satyarao, P. Rachana, Samira Sultana from A batch, first year BSc Agriculture. That's all for today's presentation. Thank you.